The Address Resolution Protocol is a telecommunication protocol used for resolution of network layer addresses into link layer addresses, a critical function in multiple access networks. ARP was defined by RFC 826 in 1982. It is Internet Standard 37 SATOM and Principe DOBAS. It is also the name of the program for manipulating these addresses in most operating systems. ARP is used to convert an IP address to a physical address such as an Ethernet address. ARP had been implemented with many combinations of network and data link layer technologies, such as IPv4, Chaosnet, DECnet and Xerox PARC Universal Packet using IEEE 802 standards, FDDI, X25, frame relay and asynchronous transfer mode. IPv4 over IEEE 802.3 and IEEE 802.11 is the most common case. In Internet Protocol version 6 networks, the functionality of ARP is provided by the Neighbor Discovery Protocol. Operating scope: the Address Resolution Protocol is a request and reply protocol that runs encapsulated by the line protocol. It is communicated within the boundaries of a single network, never routed across inter-network nodes. This property places ARP into the link layer of the Internet Protocol suite, while in the Open Systems Interconnection model, it is often described as residing between layers 2 and 3, being encapsulated by layer 2 protocols. However, ARP was not developed in the OSI framework. Packet structure: the Address Resolution Protocol uses a simple message format that contains one address resolution request or response. The size of the ARP message depends on the upper layer and lower layer address sizes, which are given by the type of networking protocol in use and the type of hardware or virtual link layer that the upper layer protocol is running on. The message header specifies these types, as well as the size of addresses of each. The message header is completed with the operation code for request and reply. The payload of the packet consists of 4 addresses, the hardware and protocol address of the sender and receiver hosts. The principal packet structure of ARP packets is shown in the following table, which illustrates the case of IPv4 networks running on Ethernet. In this scenario, the packet has 48-bit fields for the sender hardware address and target hardware address, and 32-bit fields for the corresponding sender and target protocol addresses. Thus, the ARP packet size in this case is 28 bytes. The ether type for ARP is 0x0806. Hardware type: this field specifies the network protocol type. Example: Ethernet is 1. Protocol type: this field specifies the internetwork protocol for which the ARP request is intended. For IPv4, this is the value 0x0800. The permitted PTYPE values share a numbering space with those for ether type. Hardware length: length of a hardware address. Ethernet addresses size is 6. Protocol length: length of addresses used in the upper layer protocol. IPv4 address size is 4. Operationer specifies the operation that the sender is performing, 1 for request, 2 for reply. Sender hardware address: media address of the sender. Sender protocol address: internetwork address of the sender. Target hardware address: media address of the intended receiver. This field is ignored in requests. Target protocol address: internetwork address of the intended receiver. ARP protocol parameter values have been standardized and are maintained by the Internet Assigned Numbers Authority. Example: for example, the computers Matterhorn and Washington are in an office, connected to each other on the office local area network by Ethernet cables and network switches, with no intervening gateways or routers. Matterhorn wants to send a packet to Washington. Through DNS, it determines that Washington's IP address is 192.168.0.55. In order to send the message, it also needs to know Washington's MAC address. First, Matterhorn uses a cached ARP table to look up 192.168.0.55 for any existing records of Washington's MAC address. If the MAC address is found, It sends the IP packet encapsulated in a level 2 frame on the link layer to address 00, EB24B205 ACK via the local network cabling. If the cache did not produce a result for 192.168.0.55, Matterhorn has to send a broadcast ARP message requesting an answer for 192.168.0.55. Washington responds with its MAC address. Washington may insert an entry for Matterhorn into its own ARP table for future use. The response information is cached in Matterhorn's ARP table and the message can now be sent. Arp Probe. An Arp probe is an ARP request constructed with an all-zero sender IP address. The term is used in the IPv4 address conflict detection specification. Before beginning to use an IPv4 address, a host implementing this specification must test to see if the address is already in use, by broadcasting Arp probe packets. Arp announcements. Arp may also be used as a simple announcement protocol. This is useful for updating other hosts' mapping of a hardware address when the sender's IP address or MAC address has changed. Such an announcement, also called a gratuitous Arp message, is usually broadcast as an Arp request containing the sender's protocol address in the target field, with the target hardware address set to 0. An alternative is to broadcast an Arp reply with the sender's hardware and protocol addresses duplicated in the target fields. An Arp announcement is not intended to solicit a reply. Instead, it updates any cached entries in the Arp tables of other hosts that receive the packet. The operation code may indicate a request or a reply because the Arp standard specifies that the opcode is only processed after the Arp table has been updated from the address fields. Many operating systems perform gratuitous Arp during startup. That helps to resolve problems which would otherwise occur if, for example, a network card was recently changed and other hosts still have the old mapping in their Arp caches. Gratuitous Arp is also used by some interface drivers to provide load balancing for incoming traffic. In a team of network cards, it is used to announce a different MAC address within the team that should receive incoming packets. Arp announcements can be used to defend link local IP addresses in the zeroconf protocol, and for IP address takeover within high availability clusters. Arp mediation. Arp mediation refers to the process of resolving Layer 2 addresses through a virtual private wire service when different resolution protocols are used on the connected circuits, for example, Ethernet on one end and frame relay on the other. In IPv4, each provider edge device discovers the IP address of the locally attached customer edge device and distributes that IP address to the corresponding remote PE device. Then each PE device responds to local Arp requests using the IP address of the remote CE device and the hardware address of the local PE device. In IPv6, each PE device discovers the IP address of both local and remote CE devices and then intercepts local neighbor discovery and inverse neighbor discovery packets and forwards them to the remote PE device. Inverse Arp and reverse Arp. Inverse address resolution protocol is used to obtain network layer addresses of other nodes from data link layer addresses. It is primarily used in frame relay and ATM networks, in which Layer 2 addresses of virtual circuits are sometimes obtained from Layer 2 signaling, and the corresponding Layer 3 addresses must be available before those virtual circuits can be used. Since Arp translates Layer 3 addresses to Layer 2 addresses, INARP may be described as its inverse. In addition, INARP is implemented as a protocol extension to ARP. It uses the same packet format as ARP, but different operation codes. The reverse address resolution protocol, like INARP, translates Layer 2 addresses to Layer 3 addresses. However, in INARP the requesting station queries the Layer 3 address of another node, whereas our ARP is used to obtain the Layer 3 address of the requesting station itself for address configuration purposes. Our ARP is obsolete. It was replaced by BOOTP, which was later superseded by the Dynamic Host Configuration Protocol. ARP spoofing and proxy ARP. Because ARP does not provide methods for authenticating ARP replies on a network, ARP replies can come from systems other than the one with the required Layer 2 address. An ARP proxy is a system which answers the ARP request on behalf of another system for which it will forward traffic, normally as a part of the network's design, such as for a dial-up internet service. By contrast, in ARP spoofing, the answering system, or spoofer, replies to a request for another system's address with the aim of intercepting data bound for that system. A malicious user may use ARP spoofing to perform a man-in-the-middle or denial-of-service attack on other users on the network. Various software exists to both detect and perform ARP spoofing attacks, though ARP itself does not provide any methods of protection from such attacks. Alternatives to ARP: each computer maintains its own table of the mapping from Layer 3 addresses to Layer 2 addresses. In a modern computer, this is maintained almost entirely by ARP packets on the local network and is thus often called the ARP cache as opposed to Layer 2 address table. In older computers, where broadcast packets were considered an expensive resource, other methods were used to maintain this table, such as static configuration files, or centrally maintained lists. Since at least the 1980s, networked computers have had a command called Arp for interrogating or manipulating this table, and practically all modern personal computers have a variant of this. ARP stuffing: embedded systems such as networked cameras and networked power distribution devices, which lack a user interface, can use so-called ARP stuffing to make an initial network connection, although this is a misnomer, as ARP is not involved. This is a solution to an issue in network management of consumer devices, specifically the allocation of IP addresses of Ethernet devices where 1. The user doesn't have the ability to control DHCP or similar address allocation protocols, 2. The device doesn't have a user interface to configure it, and 3. The user's computer can't communicate with it because it has no suitable IP address. The solution adopted is as follows. The user's computer has an IP address stuffed manually into its address table and then sends special packets to the device, typically a ping packet with a non-default size. The device then adopts this IP address, and the user then communicates with it by telnet or web protocols to complete the configuration. Such devices typically have a method to disable this process once the device is operating normally, as it is vulnerable to attack. Standard documents: RFC 826, Ethernet Address Resolution Protocol, Internet Standard 37 Sao Tome and Príncipe d'Obras. RFC 903, Reverse Address Resolution Protocol, Internet Standard 38 Sao Tome and Príncipe d'Obras. RFC 2390, Inverse Address Resolution Protocol, Draft Standard, RFC 5227, IPv4 Address Conflict Detection, Proposed Standard. See also, Arping, Arptables, Arpwatch, Proxy ARP, ARP Spoofing, Serial Line ARP, Sleep Proxy Service. References. This article is based on material taken from the free online Dictionary of Computing prior to November 1, 2008 and incorporated under the relicensing terms of the GFDL, version 1.3 or later. External links, up on homepage. ARP sequence diagram, gratuitous ARP, ARP-SK ARP traffic generation tools, sample capture file from Wireshark key.